Today we're going to look at some wave properties notes. I just printed out the notes as a PDF. I only left off the last practice problem so you could write it out and follow along. So mechanical waves. A wave is a disturbance that carries energy through matter or space. Mechanical waves require a medium such as water, air, ropes, or a spring. So you need matter to be present. Non-mechanical waves like electromagnetic waves do not require a medium. They can occur in space without matter. So a wave pulse is a single bump or disturbance that travels through that medium, whatever it is. And if the disturbance continues at a constant rate, you get a periodic wave. Okay, so the whole wave pattern occurs periodically. A transverse wave is one that vibrates perpendicular to the direction of the motion's wave. So over here, this wave is moving this way, but the pulses are perpendicular up and down versus the direction. A longitudinal wave is one that vibrates parallel to the direction. So the wave is moving in this direction and it's vibrating in that direction also. So sound waves are longitudinal waves. They vibrate in the air longitudinally or any other medium. And light is a transverse wave. And remember, light is not technically a mechanical wave. It's an electromagnetic wave, but it is transverse. It's perpendicular to the direction. Mechanical waves, so in a lake or an ocean, are longitudinal at the surface of the water. However, the particles move in a direction that's both parallel and perpendicular to the direction of the wave motion, as shown below. So each of the waves is a surface wave. And here's our terminology from our last video. So the highest point from the equilibrium is the crest. The lowest point from the equilibrium is the trough. And this wave motion is going in this direction. So each of the waves is a surface wave, which has characteristics of both transverse and longitudinal. So we're looking at our vocabulary again. So amplitude is how far away it is from your equilibrium point. Okay. And the crest and the trough are each separated by an amplitude from the equilibrium point. A transverse wave's amplitude is the maximum distance from the equilibrium. Since amplitude is a distance, it is always positive. Okay, even though this is below, like if we were looking at this as a graph, we would say this is negative. It's still a positive value. Waves with greater amplitudes transfer more energy. So this one has a greater amplitude versus wave B, which is smaller. So waves that move at the same speed, the rate at which energy is transferred is proportional to the square of the amplitude. So we're going to assume these waves are at the same speed. This one is double the amplitude of this one. So it would be transferring energy by a factor of 4. Okay, 2 squared. So each low point of the wave is called a trough. Each high point is called a crest. Right? Trough and crest. So to figure out the wavelength of a wave, you want to look at successive points in the wave. So the easiest way is to go from crest to crest or trough to trough. Now your X value has to be meters, okay, or some distance measurement. So you would measure from this crest to this crest. The difference is 0.8 minus 0.4. It's 0.4 meters long. If we did the trough, 0.6 minus 0.2, 0.4 meters long. Now you can also pick, a point. If we start at this point, the next successive point is here. That would be 0.9 minus 0.5, which is also 0.4. But it's just easier to look at a crest and a crest or a trough and a trough. So the speed of a wave is the distance that one wave's crests or compressions travel divided by the time it takes to travel that distance. So you also need to know the time to get the speed. So for most mechanical waves, except water surface waves, the speed depends only on the medium through which the waves move. So you can take a snapshot of the wave so you can see the whole wave at one instant in time. Our particles in the medium are said to be in phase with one another. when they have the same displacement from equilibrium and the same velocity. So any 2 points in a wave that are one or more whole wavelengths apart are in phase. So these 2 points are in phase because they're one wavelength apart. Same here. Same in this example here, the one at 0.5, the one at 0.9. Particles in the medium with opposite displacements and velocities are out of phase. So here's this, and then 180 down here, out of phase. So 2 particles in a wave can be anywhere from 0, these two, to 180 here. Okay. If you record the motion of a single particle, the motion can be plotted on as displacement versus time. So now our x-axis is time. So this would not be measuring a wavelength from crest to crest because we don't have distance on our x-axis. We have time. Here we can find the period of a wave. Okay, because our x-axis has time. So here's our period. The period of a wave is the time it takes to a point to complete one full cycle, a complete cycle. So the frequency of a wave, f, it's also sometimes is symbolized as nu, but we're going to use f, is the number of complete oscillations it makes each second. Okay. Our frequency is measured in hertz. It's pronounced hertz. The symbol is capital H, lowercase z, and then it's one oscillation per second. So it's 1/seconds is a hertz, 1 hertz. The frequency and period of a wave are inversely related. So you can calculate the frequency if you know the period. The symbol for a period is capital T. You divide 1 by the period, you get frequency. If you know frequency, you can divide 1 by frequency and you can get the period. So they're inversely related. Both the period and the frequency of a wave depend only on its source. They don't depend on the wave's speed or the medium that it's in. So the wavelength, wave speed, and frequency are related. So wavelength is speed divided by frequency. You can also say, it's very commonly said, speed equals wavelength times frequency. That's just rearranging, right? Multiply both sides by frequency. So you need to know wavelength, you need to know period or frequency. If we know the period, we can divide 1 by the period, we can get the frequency, and then we can calculate speed. So let's look at this example problem. We have a 855 hertz wave moving through an iron rail. So this is the medium. It's going through a solid made of iron, at a speed of 5,130 meters per second. So they want to know the wavelength of the wave. They want to know the period. So things that we know, we sometimes do our guess method. Here's our given, our known. We know the speed is 5,130 meters per second. We know the frequency is 855 hertz. They want us to find, here's our unknowns, the wavelength and the period. So here's our equation. Speed equals wavelength times frequency. We plug in, we just rearrange, wavelength equals speed or velocity over frequency. Plug in our values. We have a wavelength of 6 meters. Okay. Then they want to know the period. The period just can be calculated by the inverse of the frequency. So 1 divided by 855 hertz is 0.00117 seconds. Period is always measured in seconds. And if you remember, a hertz is 1/2. So if we have 1/1/2, when you have a denominator in the denominator, you flip it up to the numerator, and that's how we can get the seconds here. So review this problem, let me know if you have any questions, and then use this example to help you with the worksheet problems.